Hey guys, it's me again. Back to finish off the Chapter 11 lecture notes. So I'm resuming on page 41, and you really need to have watched the previous lecture in order to understand this one. So if you haven't already, then you need to watch that one first. All right, so we're on the last type of inequality that we're going to solve in this section. Rational inequalities. And the overall method is very similar to the polynomial inequalities that I covered previously, in other words, using the test point method. But rational functions are a little different from polynomial functions. So I just want to review what they are really quickly and discuss what the graph of a rational function looks like. Okay, so previously, either in this class or maybe in previous algebra classes, you have studied rational expressions. Okay, so rational expressions are when you have, say, one polynomial, I'm just going to write poly, divided by another polynomial. Okay, so that would just be a rational expression. And a simple example of a rational expression would be something like 3 minus x over x plus 5. Okay. So that's just a rational expression. If we want to turn that into a rational function, we just make it a function. Then we say, okay, the function f of x is equal to 3 minus x over x plus 5. Okay. And we can generically refer to this as, say, capital letter P over capital letter Q, where P is some polynomial and Q is some polynomial. Okay. Now let's add an inequality, because that's what we really want to talk about is inequalities. So let's say we write 3 minus x over x plus 5 is less than or equal to 0. Okay. So what I have just written there is an example of a rational inequality in standard form. Okay. So in general, to have a rational inequality in standard form, you would have your rational inequality, some P over some Q on the left-hand side. Then you would have some inequality symbol. In this case, I happen to have less than or equal to. It could be less than, it could be greater than, it could be greater than or equal to. And then all we want on the right-hand side is a 0. Okay? So what we want to find to solve this problem is, for what values of x is this less than or equal to 0? Okay, that's the whole question. All right, I'm going to erase this and scooch it down. All right, and I know you haven't studied the graphs of rational functions yet. You will do that if you take Pre-Calc 1, but you should be able to look at this rational function and tell me, what is the domain of this function? That is something that's covered in this class or a previous algebra class. What is the domain of this function? Okay? And the key thing with rational functions like this is that the denominator cannot equal 0. So then basically you always ask yourself, well, what value would make that denominator equal to 0? Well, that denominator will equal 0 when x equals -5. So therefore, for the domain, basically we have to exclude the value of -5. All right, so if you were going to write that in interval notation, it would be -∞, comma, -5, paren, union with, paren, -5, comma, positive infinity. In other words, every other value except for -5. Because if I put -5 in for x, I get 0 in the denominator, and of course division by 0 is not defined. Okay? So this is a plot of this function, 3 minus x over x plus 5. So what happens at x equals -5? So let's see, it's a little tough to tell. Looks like this is -4, -8, so -5 is about here, right? So what happens at x equals -5 is you end up with this thing called a vertical asymptote. Let me just sketch that in. It's kind of like this up and down line. Through, you know, the undefined value for the domain. And the function can never go across that line because x can never equal -5. Okay? And this is just a typical characteristic of rational functions. All right, so the vertical asymptote is at, let me just add that right here, x equals -5. And then we want to do the same thing we did for the polynomial inequalities, is we want to split up the number line, basically the x-axis, okay? And we're going to split it up into intervals based on two things this time. First of all, the zeros of the function, okay, that's where the graph crosses the x-axis, which is exactly the same thing we looked at above for the quadratics and the polynomials, but also now for the vertical asymptotes. Okay. And again, those occur where the denominator equals 0. All right. Now, again, this isn't the best graph in the world, but can you tell from the graph where the function is equal to 0? Where is y equal to 0 on this graph? All right, and if you look really carefully, you can see it's right about here. That is where the graph crosses the x-axis. Okay, in other words, at the point 3, 0. Okay, and notice that that is where the numerator of the function equals 0. So the 0 of the function is at x equals 3. Okay. And again, that is where the numerator of the function equals 0. So now we can split up the number line into intervals. So from -∞ up to the vertical asymptote at -5. And then from the other side of the vertical asymptote, -5 up to 3. And then from 3 up to +∞. Okay? All right, I'm going to erase and scoot to the next page. I think. Yes, okay. All right, and basically the method for these rational inequalities works exactly the same as it did for the quadratics or the cubic polynomials. The rational expression function will have a constant sign, either positive or negative, within each interval determined by the real zeros of P, remember that's the numerator, and Q, remember that's the denominator. Okay? So we're going to be finding the zeros of both the numerator and the denominator to divide the number line into intervals, but the zeros play different roles in this case. At the zeros of P, and again, that's the numerator, the function value y will equal 0. Okay? We just saw that on the previous page at the point 3, 0. Okay? At the zeros of Q, remember, that's the denominator, the function value is undefined. Therefore, there will be a vertical asymptote, like I drew on the graph. Okay? Because again, if your denominator equals 0, you can't do that. Division by 0 is not defined. So the function value is not defined. Okay? All right, so the basic method is this. Start by putting your rational inequality into standard form. And again, standard form is we have one polynomial over another polynomial, and then you're going to have some inequality symbol, and then you're going to have 0. So all stuff, inequality, 0. And again, your inequalities could be less than or equal to, greater than or equal to. Next step, find all your zeros separately for your numerator and your denominator, simply by just setting each one of them equal to 0 and solving. Which values make those equal to 0? Draw yourself a number line, just like we did before. Okay? Just mark all your zeros. That will divide your number line into intervals. And then just like we did before, choose a test number in each interval. Find the sign of the function in that interval. And then based on your signs, write the solution to the inequality. Okay. All right, so just a couple important notes. The zeros of the denominator can never be included in the solution. Okay? Even if the inequality is, say, a less than or equal to or a greater than or equal to. Because division by 0 is undefined, so these values, these zeros of Q, are not even in the domain of the function. Therefore, you cannot include them in the solution set. So what I do when I'm drawing my number line is I just remind myself, I automatically put an open circle at the denominator zeros. Not only do I do that, so I usually put an open circle, and then I also often will just draw a dashed line through it to remind myself that's a vertical asymptote. That value is not in the domain. I cannot include that value in my solution. All right, so next page. Before we actually do the analytic solution, let me just look at the graph one more time. So on the previous page, we had already noted that there was a vertical asymptote at x equals -5. So let me sketch that in again. And then we had already noted that there is a 0 at the point 3, 0. Okay? And then all of this divides the number lines into intervals. -∞ to -5, -5 to 3, 3 to +∞. Okay? And then within each interval, the output of the function, the y value, is always going to be positive or it's always going to be negative. So for example, we can see in this interval, the -∞ to -5, all of those y values are negative. Okay? And we can also see, it's a little bit harder, but we can see in this interval, above 3, x equals 3, and up to infinity, the y values here are always negative. Okay? And then in the in-between portion, between -5 and 3, right here, look, y is always above the x-axis. All the values of y here are positive. Okay? So specifically what we are looking for in this problem is where is the function less than or equal to 0. Let me just focus on the less than part. So where is it negative? Well, here and here. Okay? So this whole interval, and then this whole interval, and then also this point, because this point is where it equals 0. So if we wanted, we could actually, just from the graphical analysis, we can just write the solution. So it's going to be -∞, comma, -5. And remember, there's no function value actually at -5, so I don't include that value. And then union with, well, there is a function value here at 0. So now I need a bracket at 3, comma, infinity. Okay. So that would be the graphical solution. All right, so I'm going to get rid of all that, and then we're going to go through the analytic solution. All right, so first step, set p equal to 0. Again, p is the numerator. So 3 minus x equals 0 when x equals 3. Okay, so that is the 0 of the function. In other words, that is the value of x, the only value of x, that makes y equal to 0. Second step, set q, the denominator, equal to 0. X plus 5 equals 0 when x equals negative 5. Okay, so that is where the function is undefined. Okay, the function is undefined and there is a vertical asymptote, the line x equals negative 5. All right, so just looking at this again, 3 minus x over x plus 5, using what we just learned. Now we're going to draw our number line. Negative 5, again, that's where the denominator is 0. So my solution can never include that. So to remind myself, I kind of do a circle and a dotted line. And then at 3, that is the 0 of the function. So this is 3, this is negative 5. Okay. That divides our number line into 3 intervals. So we have the interval negative infinity to negative 5. We have the interval negative 5 to 3. And we have the interval 3 to positive infinity. All right, exactly the same test point method. Within each interval, I'm going to pick a test value. So I'm just going to pick negative 6 in this interval. I'm going to pick 0 in this interval. And I'm going to pick 4 in this interval. Okay. F of x. Okay, so in other words, if you wanted, you could calculate, well, what is exactly the value, say, of f of negative 6. All right. And again, I showed you guys this method the other day, how I don't really care what f of negative 6 is. I just want to know, is it positive or negative? So let me just come over to the side here, and like if we were going to do f of negative 6. So in other words, I'm going to just substitute in x equals negative 6. So I'm doing 3 minus a minus 6 over minus 6 plus 5. All right. So without actually calculating the number, even though it's fairly easy for this one, 3 minus minus 6 turns into 3 plus 6. Or in other words, it's positive 9, but let's just note that it's a positive number. Negative 6 plus 5. So that's negative 1. Okay, that's a negative number. So in other words, f of negative 6 ultimately is going to be a negative number. And that's really all I care about. So let me just make a note that it is negative. And then let's come over and do the same thing for the next interval where our test value is 0. So if I were to substitute in x equals 0, and again, I'm just substituting it into the function. So in other words, 3 minus 0 divided by 0 plus 5. Okay. All right, so 3 minus 0 is positive 3, so it's positive, over 0 plus 5 is 5, it's also positive. So positive divided by positive, all right, so within that interval, all of my output values are going to be positive. That's all I need to know. And then finally, the last interval, we picked our test point of x equals 4. So if I were going to do f of 4, substitute in 4 for x. So I would have 3 minus 4 over 4 plus 5. Okay, so 3 minus 4 is negative 1, so that's negative, divided by 4 plus 5 is positive 9, so that's positive. So negative divided by positive is negative. All right, negative. The solution, all right, now let's carefully go back up and look to the problem. It wants to know where is it less than or equal to 0. Okay, well, in this interval, it's less than 0. In this interval, it's less than 0. And at this point, it's equal to 0. So I need to include this interval, but not this point. The function is not defined there. And then this point and this interval. Okay? So in other words, negative infinity to negative 5, paren, union with, and then I'm going to do a bracket, a hard bracket, because I want to include that 0.3, comma, up to infinity, paren. Okay? I'm going to pause for a minute and then erase everything. Okay, so just a quick comment down here at the bottom of the page, how to put an inequality into standard form if it isn't already. Now, most of the problems in the book, I noticed, are already in standard form, like the problem we just did, where it already has inequality, here's your rational inequality, here's your symbol, and then they have a 0 on the right-hand side. Most of them are like that. In the event that you get something that isn't, like this one is not, because it doesn't have a 0 on the right-hand side. Therefore, we have to get it into that right form before we can use the methods to start and solve it. So just in the event that you would get a problem like that, I want to make sure you know what to do. Okay, so again, we have to get a 0 on this side. So just using, basic algebra, the first thing we need to do is subtract that 5 from both sides. So now what I have on the left-hand side is I have 3 minus x over x plus 5 minus 5. And I'm going to deliberately leave a little space here, is less than or equal to, and now on this side I now have 0, which is exactly what I want. Okay? But now on the left-hand side, I need to get all of this into a single expression, one polynomial divided by another polynomial. So in other words, I need to go to the least common denominator, which would be x plus 5. So I got to multiply this guy by x plus 5 over x plus 5. And remembering in the numerator that I'm going to have to distribute and be careful to distribute that negative sign. So we've got 3 minus x, and then I've got minus 5 times x, so minus 5x. And then I've also got minus 5 times 5, or in other words, minus 25. And now all of that is over that common denominator of x plus 5. And then we've got the less than or equal to 0. Okay. And then the last step we would want to do is combine those like terms. So for example, I've got minus 1x minus another 5x. That's going to be minus 6x. And then I've got 3 minus 25, so that's going to be minus 22. And that's all over x plus 5. And it is less than or equal to 0. Okay. So that's what we want. Now we're back to that standard form, which is I've got one polynomial over another polynomial, and then I have my symbol, and then I have 0. Okay, so I'm not going to solve that. I just wanted to show you how to get it into the right form to solve it if you need. All right, I'm going to erase that. All right, so on the last 2 pages here, I have some problems. I would like you to pause and try to solve these. So this is a polynomial, a quadratic inequality. We did one just like this. This is a polynomial or a cubic inequality. I did one just like this. And this is a rational inequality. This is what I just did. So please do pause this for a few minutes. Try those problems by yourself, and then I will come back and run through the solutions. All right, so let me get back to these practice problems that you guys have already done, right? Okay, so the first one is a quadratic inequality. Where is x squared plus 6x plus 9 greater than 0? Okay, so the first thing you should do is just factor this. It's pretty easy. It's just x plus 3 times x plus 3. So then if we were to ask ourselves, well, where is that equal to 0? Well, there's actually only one 0 at negative 3. Okay, this is a double root. All right, so the quadratic equals 0 at negative 3. So on our number line, this is kind of handy because we only have one 0 at negative 3. Therefore, we only have 2 intervals. Okay, so from negative infinity to negative 3, and then from negative 3 to infinity. All right, and then in each interval, if you want to pick a test point, let's see, I would just pick negative 4 in this interval, and I would pick 0 in this interval. And then, you know, we could actually calculate the value of f of x. So what is the function when x equals negative 4? Just plug it in here. Again, all we really want to know is what is the sign of f of x in that interval. So let me come over here. So when x equals negative 4, I'm just going to substitute that in. So I'm going to have negative 4 squared plus 6 times negative 4 plus 9. All right, so negative 4 squared is 16, and then minus 24 and plus 9. All right, so 16 plus 9 is 25. 25 minus 24, it's plus 1 is the value. But the point is that the value is positive. Okay? So everywhere in this interval, the sign of the output is going to be positive. All right, now let's go to our other test point in this interval, which is x equals 0. This one's easy because it's 0. So in other words, 0 squared plus 6 times 0, so both of those are just 0, and then plus 9. So the value is going to be plus 9, and the sign is positive. Okay, positive. And what are we looking for? We're looking for where is it greater than 0, but not equal to 0. So remember, at this point, it is actually equal to 0. So I don't want to include that point, but I do want to include this entire interval and this entire interval. So we have to write it as, well, this entire interval, negative infinity, negative 3, paren, because I don't want to include negative 3, and then union with paren, negative 3 to positive infinity. So in other words, everything except for negative 3. And if you think about the function, x squared plus 6x plus 9, it's a quadratic, and we know that a is greater than 0, so it's going to open up. And we discovered that it only has one 0, in other words, only one x-intercept. So, the plot of that, if this is the negative 3, is basically going to look like this. Okay? And again, the whole point of the question was, where is the function, the y value, positive? Well, everywhere here and everywhere here. And that's exactly what we just found analytically. Okay, pause if you want. I'm going to erase all that and move on to the next one. All right, so this is a polynomial inequality. This, if you multiplied it out, would be a cubic, but the ones they've got in the book here, they have them all factored for you. Okay, so we want to find the zeros. We've got x minus 2 times x minus 3 times x plus 1. Where is that less than 0? Where is it negative? Well, first find the zeros. Where is this equal to 0? Well, at x equals 2, or at x equals 3, or at x equals negative 1. Okay, so that gives us our points for the number line. So we're at negative 1, 2, and 3. All right, so we can list our intervals. All right, so from negative infinity to negative 1, and from negative 1 to 2, and from 2 to 3, and from 3 to infinity. Okay, within each interval, pick a test value. So here I'm going to pick x equals negative 2. Here I'm going to pick 0. Here it's got to be between 2 and 3, so I'm going to pick 2.5 or 2.5. And here I'm going to pick 4. Okay. And then either go all out and actually calculate the value of the function, or just figure out the sign of the function. I, of course, am just going to figure out the sign. All right, so let's start with x equals -2. I'm going to come over here. So if we plug in x equals -2 to the function over here, so we're going to have -2 minus 2 times -2 minus 3 times -2 plus 1. All right, let's just figure out the sign of each of those. So -2 minus another -2, that's going to be negative. -2 minus another 3, that's going to be negative. -2 plus 1, that's still going to be negative. Okay, so in other words, I have a negative times a negative times a negative, which is going to wind up being a negative number. That's all I need to know. All right, so the sign of f of x in that interval is negative. All right, for x equals 0. And let's plug that in. So I've got 0 minus 2 times 0 minus 3 times 0 plus 1. Okay, let's look at the sign. 0 minus 2, that's negative. 0 minus 3, that's negative. 0 plus 1 is positive. So I've got a negative times a negative times a positive. All right, so that's going to be positive. All right, let's move on to x equals 2.5. Okay, substitute that in. So I've got 2.5 minus 2. And then I've got times 2.5 minus 3. And then times 2.5 plus 1. All right, let's look at the sign of each of those. 2.5 minus 2, that's positive because 2.5 is bigger than 2. 2.5 minus 3, that's negative because 2.5 is less than 3. 2.5 plus 1, that's positive. So I've got positive times negative times positive. All right, that's going to be negative. All right, last test point is x equals 4. All right, let's substitute that in. So I've got 4 minus 2 times 4 minus 3 times 4 plus 1. All right, so this is positive, positive, positive. They're all positive, so this is obviously going to be a positive result in that interval. All right, let's go back and see what we are looking for. We are looking for where is this less than 0. Not equal to 0, just less than 0. So that's going to be in this interval, and we are not going to include the endpoints here or here because that is where it equals 0. So I just want the two intervals. So in other words, negative infinity, -1, union with, and then this interval is 2, 3. Okay, and let me erase all this stuff, and I'm going to pull over a graph of this function to show you. Okay, so this is what the function looks like, and you can see right here the zeros that we had identified at x equals -1, x equals 2, and x equals 3. Okay, those were the zeros we had put on our number line. And then again, the problem was to look for where is this function less than 0? Where is the output of the function less than 0? Where is y negative? Well, here and here. Okay? And that's exactly what we just found analytically, is that it was in this interval and this interval. Okay? From negative infinity to -1, and then also from x equals 2 to x equals 3. Okay, last one. So this is our rational inequality. And notice that we already have it in the standard form. We already have P over Q. And then we have our inequality symbol. It happens to be less than or equal to. And we already have 0. So we don't have to do anything to this other than just start. Okay, so remember the first step is to find the zeros of the numerator, P. So in other words, where is 5 minus 2x equal to 0? Okay, well that would mean that 2x is equal to 5, or x equals 5/2. Okay, so because that's a 0 of the numerator, then that is the 0 of the function. Okay, so in other words, the point 5/2, 0 is on the graph of this 5 minus 2x over 4x plus 3. Second step, find the zeros of the denominator. All right, so where is 4x plus 3 equal to 0? Okay, so then 4x equals -3 divided by 4. So when x equals -3/4. Okay, so that is where there is a vertical asymptote. Okay, in other words, the function is not defined at that point. Okay, it's not defined because you cannot put in a value of x equals -3/4 because that would make your denominator equal to 0, and you can't divide by 0. It's not defined. Okay, so that value is not even in the domain of the function. All right, so then referring to these two values, we draw our number line. So I've got my undefined value at -3/4, so I'm going to mark it like this, and with a little dashed line, just so I remember. So that's -3/4. And then up here at 5/2. All right, so that defines our intervals. So we're -infinity up to -3/4. And then -3/4 to 5/2. And then 5/2 up to infinity. All right, pick a test x value in each interval. Okay, so the next more negative integer would be -1, so that seems easy. Pick x equals -1. In this interval is x equals 0, so always pick that if you can, it's easy. And then 5/2 is 2.5, so the next bigger integer would be x equals 3. Okay. And then either calculate the exact value of f of x or just find the sign of f of x. All right, so let's start with x equals -1. I'm going to come over here. So I'm just going to take -1. I'm going to plug it into this. All right, so 5 minus 2 times -1 divided by 4 times -1 plus 3. So 5 minus -2 turns into 5 plus 2, which is 7, so that's positive. -4 plus 3 is going to be -1, so that's negative. Positive divided by negative, that one's going to be negative. Okay, so this interval is negative. All right, let's move on to the next one, x equals 0. So I've got 5 minus 2 times 0 divided by 4 times 0 plus 3. All right, so 5 minus 0 is 5, so that's positive, over 0 plus 3 is 3, that's positive. All right, positive over positive, it's going to be positive in that interval. All right, our last interval, our test point is x equals 3. Okay, substitute that in. So we have 5 minus 2 times 3 divided by 4 times 3 plus 3. So 5 minus 6 is negative, over 12 plus 3 is positive. Okay? Negative over positive, it's going to be negative. Negative. Okay? All right, and let's remind ourselves what we're looking for. Where is it less than or equal to 0? Well, it's less than 0 here, it's less than 0 here, and it is equal to 0 here. So I don't want to forget to include that point in the solution. But I can't include this point because this point, the function is not even defined. So let's see, it's going to be this interval, which is negative infinity to negative 3/4, paren, because I'm not including that value, and then union with, now I am including 5/2, so I have to do a bracket, 5/2, comma, infinity. So that would be the solution for that one. All right, pause for a minute if you want. I'm going to erase this. I'm going to pull the graph over for this function. So I've got a graph of 5 minus 2x over 4x plus 3. Right here. All right, and so just like we saw when we did it analytically, so here is the vertical asymptote. So this is at x equals negative 3/4. So the function is not defined there. There is no function value. So that was the first value that split up our number line. Here's the 0 at x equals positive 5/2. So that's the second value that splits up the number line into the 3 pieces. Okay. And then remember, we were looking for where is it less than or equal to 0. Or, in other words, where is y less than or equal to 0. Okay. Well, you can see it, this whole portion of the graph in this interval, okay, y is negative. And then here it is positive. Oops, I moved my intervals. Sorry about that. Let me scoot this back over. Where was it? Like this, right? Yeah. Oh, crap! Never mind. Okay. This portion here, it is above 0. And then here, y, again, is negative. And at the point there, it is equal to 0. Okay. So again, that's why we included from negative infinity up to here, and then from 5/2 up to positive infinity. Okay. All right, well, I hope very much that I will see you guys next week. And any questions on the quiz or on the new assignment, just let me know.